So in case of the first part of question 1a, you will require to find the value of T naught, which is shown in the figure here, corresponding to an instantaneous voltage of 10 volts, which is marked here. So if we look into this waveform, the expression for the voltage is given as 20 sine omega t, which means that the maximum value for this, or the peak value of this waveform, is 20. So we can mark this as 20 and this is minus 20 volts. And we in fact will be doing a sort of reverse engineering from this expression, and since we know that at time t naught the voltage value is 10, so we are going to substitute in place of small v the instantaneous value 10, and in place of t as t naught, while omega becomes 100 pi, because the time period capital T can be evaluated is 0.02 seconds, and thus the frequency, which is written as 1 upon capital T, f is 50, and then from there we get omega, which is 2 pi f as 100 pi. And this can in fact be further written as sine of 100 pi t naught is equal to 10 by 20, which is 0.5, and further this can be written as 100 pi t naught equal to sine inverse of zero point 0.5, which is pi by 6, and thus this gives us t naught as 1 by 600, which is 0.00167 seconds. Now again, in the second part of this question 1a, it asked about two alternating voltages which are given by expression v1 60 sine omega t, the other is v2 40 cos omega t minus 60. So note that here that the voltage v2 is given in terms of cos, and thus we are required to first convert this into sine waveform, and then we're going to compare it. So v1 is given as 60 sine omega t, and this can in fact be written in terms of polar form as 60 angle 0, while v2 is in terms of cos, so we have 40 cos omega t minus 60. So we can in fact convert this into sine in order to compare it with v1. So this gets as 40 cos omega t plus 90, and thus this can be written as 40 angle 30 degree in polar form. And as compared to v1, we see that v2 makes an angle of plus 30 degree, which is drawn here, and have a magnitude of 40. So this is the required answer of the phasor diagram asked in the question. And again, third question, which was about calculating the RMS value of the current waveform as shown in figure 2 here. So we see this in the figure 2. We have a sort of sawtooth wave, and as I told you that in order to find the RMS value, you'll have to first identify the cycle. So the cycle for this particular waveform is from 0 to capital T, as it starts repeating itself from T onwards. So the cycle of this is identified as 0 to T, and RMS value, we use the formula for RMS value, which is given as under root of the integration from the 0 to T, which is the period of the cycle, the waveform, I square dt divided by capital T minus 0, the period during which we are interested to find the RMS value. And in order to know the value of current during this period from 0 to t, we know that the expression for straight line is given as y equal to mx plus c, where m is the slope of the line and c is the intercept. And since we have 0 intercept in this case, so c is 0, and we'll be finding the slope of this particular line using the well-known standard form y2 minus y1 divided by x2 minus x1, where y2 is im and y1 is 0, while x2 is capital T, x1 is 0. So this gives the slope of the line as im divided by capital T, and thus the equation for that particular sawtooth wave from between 0 to t can be written as I equal to im by capital T into t, which is y equal to mx plus c. C is 0. And thus if we substitute this value back to this particular equation, what we get is the RMS value of current can be written in this form, and we further apply the things that we already studied, like integration and substituting the limits. So what we get is im divided by root 3. Now again, in another question 1b, it was asked to find the current flowing through the galvanometer G having resistance 50 ohm as shown in this circuit. So this is the galvanometer where we are interested to find how much current flows through it using Thevenin's theorem. So in order to solve this, what we do is we first replace we use a resistor, because the resistance of this galvanometer is 50 ohms, and we place a 50 ohm resistor in place of G. And then the first thing is to evaluate RTH, or VTH can also be evaluated. That all depends upon you. So we first evaluate RTH by removing the resistor through which the current is desired, and then short circuiting the voltage source. And in order to, it's the arrangement shown over here is a simple parallel and series resistance combination that we need to figure out. And then if we try to analyze this circuit, so this circuit can in fact be rotated anti-clockwise to get a circuit shown over here. And if we further try to simplify this, the circuit can in fact be drawn in this manner, where what we get is 30 and 10 ohm resistors to be in parallel, similarly 40 and 20 ohm resistors to be in parallel, and their parallel combination can then be evaluated. So the parallel combination of 30 and 10 is 7.5, while that of the 40 and 20 parallel combination is 13.33. And thus the RTH, which is the resistance between A and B, can be written as 20.833 ohms. Now we evaluate VTH. So VTH is comparatively easier in this case. So what we do is we consider a loop where, accompanying this voltage source, then this 10 ohm resistor and this 30 ohm resistor. So if we consider this outer loop and apply KVL to it, what we get is, I'm moving anti-clockwise starting with this voltage source. So from minus to plus, what we get is 100. Then we have I1 entering this point, so this can be taken as plus, and this as minus. Similarly, we assumed I2 current in the second branch, so this is taken as plus, this is minus, this is plus, this is minus, this is plus, and this is minus. So again we apply KVL to this. So this is minus to plus 100 volts, and plus to minus I1 10, then plus to minus is minus I1 30, which is equal to 0, and then we get I1 as 2.5 amperes. And in the bottom branch we have current simply I2, which flows through 20 and 40 ohms resistor. So if we apply KVL to this loop in which we have bottom branch, so we have minus to plus as 100, minus I2 20 minus I2 40 equal to 0, which gives us I2 equal to 1.667 amperes. Now in order to find VTH, what we do is we can apply KVL to this left side triangle or the right side triangle. So let's apply this on the left side loop. So starting again anti-clockwise from this particular point, minus to plus, plus VTH, minus to plus 10 times of I1, again with a plus sign. So VTH plus 10 times of I1 was evaluated in the previous step. Then again from plus to minus is minus I2 into 20, which is written here, and this will be equal to 0. So we substitute the values of I1 and I2 evaluated in the previous steps to this particular expression, and what we get is VTH is 8.34 volts. Now we redraw the Thevenin's equivalent circuit, which comprises of VTH in series with RTH and the load resistor connected back to the terminals A and B. So I forgot to write A and B terminals here. And is now easy to evaluate the current that flows through the circuit, which is simply I equal to VTH divided by the values of RTH plus RL, which are connected in series, and this gives us the current as 0.1176. So this is the amount of current that flows through the galvanometer in the given question. Now the next question was a combination of series parallel combination circuit is given, and we are required to find the total admittance of the circuit and the power consumed in each branch. So in fact we need to apply the simple relations of R, L and C. We will have to find the impedances that we learned in the classroom. So we have a resistor in series with inductor, so the impedance of this branch can simply be written as ZA. We assume this branch as A, so let's mark this branch as A and this as B. We assume this branch as C, and let's mark the series branch as D. So the impedance for branch A is 2 plus the impedance of this inductor, which is x j times of XLA, and XLA is 5 ohms. So impedance of branch A is 2 plus 5 j 5 ohms. Similarly, the impedance for branch B can be evaluated since it includes a capacitor. So we will be finding the reactance of this particular capacitor, and with the minus sign multiplied by j gives the impedance of the capacitor. So ZB is 0.5 minus j XC. For the third branch C, it simply consists of a resistor, so the impedance of this branch is simply 1. And for the fourth branch D, we have the resistor in series with an inductor, so the impedance of this branch can in fact be evaluated in the same way that we did for the branch A, and thus the impedance of branch D is 0.4 plus j 0.8 ohms. Now the admittance is simply reciprocal of impedance. So for branch A, the admittance comes out as 1 upon ZA, which is written here, and then YB, the admittance for branch B, and YC for branch C. So the admittances for each of these branches are evaluated, and since they are connected in parallel, so we know that for branches that are connected in parallel, their admittance can in fact be simply added together. So the three branch admittance is simply YA plus YB plus YC, which comes out as this value. And this parallel branch impedance can also be evaluated, that because we will be using this value in finding the current in each branch. So ZP can be written as 1 upon YP, and thus ZP comes out as 0.576 minus j 0.246 in Cartesian form. And note that we in fact what we are doing here is we are using calculator to convert this Cartesian form to polar, then from that polar form back to Cartesian form. Similarly, what we did here, we didn't show these steps involving the conversion from the Cartesian to polar and back to Cartesian form, but we have shown a step here. For example, this is the Cartesian form that is converted to polar form here, and then again 1 divided by this value gives 0.626, the rules that usually apply to Cartesian and polar calculations. And then this polar form is again converted back to Cartesian form. Then what we do is, since we find ZP, which is nothing but the impedance of this three branches, and after obtaining the impedance of these three branches, the impedance is connected in series with ZD. So we evaluate the total impedance, which comes out Z parallel plus ZD, which is in polar 1.122 angle 29.58 degrees ohms. And similarly, to find the total admittance of this circuit, we'll simply divide, or we'll take the reciprocal of Z total, which is 1 upon Z total, and this comes out as 0.891 angle minus 29.58 degree Siemens. The total current can also be evaluated by dividing the source voltage divided by the total impedance, and this gives us 89.13 angle 29 minus 29.58 degrees amperes. And the voltage across parallel combination can be evaluated using this I total, because I total is the current that flows through the source and it passes through this combination, the parallel combination of branch A, B and C. And since we evaluated the equivalent impedance of these three branches, so it is then assume that the current from the source will be passing through the combination impedance of these three parallel branches, and thus the voltage across this parallel branch will be I total multiplied by ZP. So VP comes out as the voltage that appears across the three parallel branch, and the value is given here. Now to find the current that flows through the branch A, we have the voltage that occurs across that branch divided by the impedance of that branch, which is 10.36 angle of this. And similarly, the voltage divided by for second branch is voltage divided by ZB, which gives us IB as this value, and then IC comes out as this value. And the power can in fact now be evaluated, since power is given as I square R. Since the question asks about consumption of power, power is normally, as I told you in the classroom, the power is consumed only by the resistor. So it means that the question asks about the power that is being consumed or being dissipated, so which is normally done by resistor. So in branch A we have one resistor of 2 ohms, and the current we found was 10.36 amperes. So I square R gives us 214.6 watt, which is being dissipated or consumed in branch A. Similarly, in branch B, you have this amount of power which is being consumed. In branch C, this is the power that is being consumed. Finally, the branch D will be taking the value as the total current that comes out from the source, because for branch D, whatever current comes out from the source is passing through branch D and back to the source. So that is why the total current is square multiplied by the resistance in the branch D, which gives us 3177.6 watts. Similarly, the question based on the three-phase circuit, and we have a star connected system on the left side and delta connected load on the right side. So since we need to find the current that flows through the loads, so we need to evaluate the voltage that appears across the loads. So between this particular point and this point is the voltage that comes from the point small a and point small c from the source. So we know that VAN is the line voltage for this star connection given as 100 angle 10 degree. So VAC is the voltage that should appear across the point A and B for the delta connection. So this point is connected here and C point is connected here. So whatever voltage occurs across A and C, small a and C, will occur across the points small a and B, capital A and B. So the voltage between A and C is the line voltage, while VAN is the phase voltage. So the line voltage can in fact be evaluated by taking root 3. The magnitude is simply root 3 times of the phase voltage. So root 3 multiplied by 100 would give us the line voltage, and the angle can in fact be evaluated by using the phasor diagram that we saw in the classroom. So since the angle is 30 degrees for the line voltage, and thus this can be written as 100 angle 3 10 plus 30 degree, and thus this can be written as 173.2 angle 40 degree. And using this expression, we can find the phase current as this voltage divided by the impedance, which is 8 plus J4 in each load branch, and thus voltage divided by impedance gives us the value of current in this form. Similarly, IBC will have the same magnitude, but the phase will be shifted by an angle of 120, shifted from 13.43, which gives us as minus 106.57, minus 120. And again, similarly, we have minus 120 further shift from minus 106. So we can write this as minus 106 minus 120 in place of this value, or we can write plus 120 with respect to this value. So if we add 120 to this, what we get is 120 to this value. So this ICA is shifted by an angle of plus 120 to this. So if we add 120 to this, it gives us 133.43 degrees. So rest of the questions that were asked in the exam were based on theory. So that can easily be referred to notes.